Welcome to the walkthrough of Part 1 of Assignment 4. The purpose of this assignment is to deepen your experience using Java functional programming features and their integration with Java reactive streams. In particular, for this assignment, you'll develop an app that uses the Project Reactor implementation of reactive streams to obtain, transform, and store images. Like the earlier assignments, the code you'll write here will have a GUI and will run as an Android client app that can either perform all image processing locally on the client device running Android, or perform all the image processing remotely using reactive microservices that can be deployed on one or more servers and implemented via Spring WebFlux. Please use this GUI along with the unit test discussed below to help evaluate and debug your solution. The following resources may be helpful in completing this assignment. A detailed overview of Java reactive streams and a comparison with streams is available here, and a tutorial overview of Project Reactor appears here. Naturally, we'll cover all this material in class. The image crawler app is packaged as a project using the latest version of Android Studio. This app is written in both Kotlin and Java and demonstrates many Android capabilities. For the purposes of this assignment, however, you only need to be aware of the following folders: Image crawler source main Java edu Vanderbilt image crawler crawlers, which contains the skeletons you need to fill in, as described below. Image crawler source test, which is a set of unit tests that exercise key features of the app and can be used to evaluate whether you've correctly satisfied this assignment's requirements. And app source Android test Java assignment tests, which is an Android Studio instrumentation test that runs your app automatically. To compile this code, you need to use the provided Android Studio project. You can run this project by clicking the green Run App button in the Android Studio IDE, which should automatically select an Android emulator to run, assuming you have one created. The app's minimum API is 29, so you'll need to select an emulator that uses an API greater than or equal to 29. If you don't already have an Android emulator, you can create one by clicking on the AVD Manager button in the Android Studio IDE. You'll need to modify several files containing the Java skeleton code by completing the to-do you fill in here tasks to provide a working solution. Do not change the overall structure of the skeleton. Just fill in the to-do tasks and do not delete the to-do tags. In particular, you'll need to finish implementing the following to-do tasks for this assignment in the image crawler source main Java edu Vanderbilt image crawler folder. Start by modifying the crawler's reactor crawler.java file. Here, you'll need to complete the to-do tasks in various methods to obtain, transform, and store images. This class uses Project Reactor Flux and Mono operators to perform an image crawl asynchronously, starting from a root URI. Depending on the parameters used to run the tests, images from an HTML page reachable from the root URI are either downloaded from a remote web server or read from the local file system, and the results are stored in files on the Android client device. Likewise, these parameters also determine whether all image processing is either performed locally on the client device or remotely using reactive microservices deployed on one or more servers. You'll also need to modify the units student.kt file, where you need to complete the to-do task to set the type field to either graduate or undergraduate, depending on which version of the assignment that you're implementing. The bulk of the code for the app is provided in the skeletons. In fact, a complete solution using Java features The bulk of the code for the app is provided in the skeletons. In fact, a complete solution using Java 7 features appears in the sequential loops crawler.java file. You will therefore focus on converting this Java 7-based class to the Reactor Crawler class that uses the Project Reactor framework. Your solution should use no loops, nor any unnecessary conditional statements in this assignment, and instead use Project Reactor Flux and Mono class operators. Your solution will be considered correct if it passes all the unit and instrumentation tests. Skeleton code for this assignment is available here in my GitHub account in the Client Skeleton folder. You can pull this skeleton code in your repository, read it carefully, and complete the to-do markers. Unit tests in the image crawler source test folder are provided to increase our and your confidence that your implementation is working as expected. You need to learn how to use the Android Studio GUI to run the unit test locally on your computer, as described here. As usual, testing only demonstrates the presence of bugs, not their absence. So don't rely solely on the unit test to detect problems in your code. This assignment is more complicated than the previous assignments, since it requires deeper knowledge of Project Reactor and remote communication via Spring WebFlux. In particular, the asynchronous nature of reactive streams may take some time to get used to, so please start the assignment soon and ask questions in class, office hours, and on the discussion forums. As usual, the app, image crawler skeletons, and unit tests are extensive, though you don't need to understand them all to complete your solution. Now that we've walked through the specification for Part 1 of Assignment 4, let's take a look at the skeletons. We'll start with the Reactor Crawler class. This class uses Project Reactor Flux and Mono reactive types to perform a concurrent image crawl starting from a root URI. images from HTML pages reachable from the root URI are downloaded from a remote web server or from the local file system, transformed, and then stored in files on the local Android client device that can be displayed to the user. We'll begin our discussion with the perform crawl entry point method, which is called by the underlying app. This method recursively crawls the given page and returns the total number of processed images. As you can see, it takes a page URI parameter that's a string indicating the URI that's being crawled at a given point, and it takes a depth parameter, which is the current depth of the recursive processing. The implementation of perform crawl should be done as follows. First, it should call the crawl page async helper method to perform the crawl asynchronously, and then it'll use a series of flux and or mono operators to obtain a count of the number of images that were downloaded and processed, wait until all the processing is done, and return the result as an int value. If any error or exception is encountered, then the value 0 is returned. Let's take a look at crawl page async. This method recursively crawls the web page passed as the page URI, and then downloads and transforms all the discovered images. The recursion will end when the passed depth is exceeded. The implementation of crawl page async should return a flux stream of images from this page and all page links recursively reachable from it. In particular, it should return an empty flux if the depth length of the web crawling is reached, or if the page URI has already been visited. This method should use flux operators like just, filter, map, and flat map. And that latter operator, flat map, should call the helper method images on page and page links async. Speaking of which, let's now go ahead and take a look at the images on page and page links async method. This should return all the images on the page and its linked pages. It should take a page parameter, that's the crawler page to crawl, and again take a depth parameter, which indicates the maximum depth of the crawl. The implementation of this method should return a flux stream consisting of all images on this page and any images linked on it. This method should call the images on page links and images on page helper methods and use flux operators merge with and subscribe on to merge all the images into a single flux stream via a parallel scheduler. Let's now take a look at the images on page links async method. This method finds all page links on the past page and recursively crawls each page to download and transform all the discovered images. As before, it takes a page and a depth. This implementation should create and return a flux stream consisting of images that have been downloaded and transformed. This method should call the crawl page async helper method recursively and use the flux operators like from iterable, flat map, and subscribe on to perform the processing on the parallel scheduler. Next, let's take a look at images on page async. This method is used to find, download, and transform all images on the given page, which is passed, as you can see, as a parameter. The implementation of this method should create and return a flux stream for this page using the flux flat map concurrency idiom. It should call the get page elements as URLs, download image async, and transform image async helper methods, as well as use flux operators like flat map and from iterable to perform processing on the parallel scheduler. The flat map operator can be called more than once. The next method we'll look at is called download image async, which, as you might expect from the name, asynchronously downloads and returns an image at a given URL. This method should be implemented by creating and returning a mono instance that emits the downloaded image at the specified URL. It should call the helper method get or download image, as well as use mono operators like from callable, map not null, and subscribe on to perform processing on the parallel scheduler. The other operator along the same lines is called transform image async, which routes the image transform request to either a local or remote transform image handler. As you can see in this implementation which we provide, it checks a flag that's set by the GUI to determine if the transform should be run locally or remotely. So you can see we have a local implementation and a remote implementation. So let's go ahead and take a look at those two implementations, starting with the local one. Transform image locally should locally apply, in other words, on the client device, the current set of crawler transforms on the image that's passed as a parameter, and then return a flux stream of all successfully transformed images. The implementation of this method is fairly straightforward. It should perform the transforms locally and return a flux stream of transformed images by calling the create new cache item and apply transform helper methods, as well as flux operators like from iterable, filter, and map not null. The last method here is perhaps the most interesting and most complicated one. This is called transform image remotely, and it will be used to call a remote server, which is basically an API gateway into a series of microservices that are implemented using the reactive Spring WebFlux platform. This will perform the transforms remotely. So let's take a look at this method. You can see it takes the image that's passed in as a parameter, and it will process the transforms remotely and return a flux stream that contains the transformed images. This method should call the build multi-part body part helper method along with the get transform names, apply reactor transforms, and create image helper methods. It should also use mono and flux operators such as flat, map, many, and map, respectively. So let's take a look and see how it's structured. Some of the parts are provided for you just to get things up and running. So the first thing we do here is we call the get API method that's defined here in the remote data source class, which is available over here. And this particular method is going to return a transform API instance. Let's take a look at transform API. Transform API is the API interface that's used by the retrofit package to create an instance that can then be used for all calls to the server that's running remotely. This would be the server API, or the API gateway as it's commonly called in reactive microservices nomenclature. As you can see here, we keep track of the string to use to indicate what endpoint method to call on the server. And then down here we have the retrofit syntax, which defines a method called apply reactor transforms, which takes a list of transforms, which are basically strings indicating what kinds of image processing to perform. And you can see there's various types. There's a tint transform and a sepia transform and a grayscale transform and so on. These are the names, and keep in mind the processing will actually be done remotely on the server. And then we also pass in something that's an image, which is of type multi-part body.part. And that's the image that will be transformed. So the image will be passed from the client app on Android over to the remote server. Now, the implementation, of course, will be done remotely. This is just essentially generating the code that will perform this operation as a post request using various HTTP clients, which we'll show you in a moment. And what gets returned from this method is a mono to a list of transformed images. So that's essentially the key method that's defined here in this class that we're going to be talking about. If we pop back a little bit, you can see that you also then create a remote source object, which we're going to be using for various purposes down below. And then we're going to use a helper method on remote source in order to build a multi-part body part that contains the image bytes. And if you go back over here to remote data source and you poke around a little bit more, you'll see it has a bunch of interesting fields and methods defined here, a couple of which are adapters for retrofit that are used to be able to either have the Reactor, Project Reactor work or RxJava work. We're, of course, using Project Reactor here. And then down here we have this factory method called build multi-part body part. And that is the method that you'll be calling here in order to be able to create a multi-part body part that will be used to contain the image bytes. Likewise, you're also going to call a helper method that's defined in the superclass of Reactor Crawler in order to get the list of transform names, which we're going to be passing over to the server. Then down here, you'll use the API that you got back up there in order to be able to invoke the appropriate operator or appropriate method, which in this case, of course, will be apply reactor transforms, passing in the right parameters. And then that will go ahead and make the call to the reactive microservice API gateway. That will return a mono to a list of transformed images, which you then must convert into a flux of transformed images. You have to use the right method in Project Reactor's classes to do that. And then the final thing you'll do here is you'll use another helper method to create an image instance from the flux of transformed images. So you basically want to return a flux of images which will be transformed from the flux of transformed images. So those are the main things you'll need to implement. Of course, to really make this work, you're going to have to get the server side done as well. So if you come back in part 2 of Assignment 4's walkthrough video, you'll get a chance to learn how to implement that part of the solution. Now that we've walked through the specification and skeletons for part 1 of Assignment 4, let's go ahead and run the unit tests. As usual, we click on the Run All Tests button, which goes ahead and builds and runs the unit tests. As you can see, there's about 10 unit tests that are independent of whether the image transforms are done locally or remotely, and these are called reactor crawler tests. They all get the little green check mark, which means they all performed correctly. There's two other types of tests here. One is the reactor local crawler tests, which do the image transforms locally, and the other one is reactor remote crawler tests, which do the image transforms remotely. Now, for this particular run, all the testing is done locally because we're using mocking. But when we get to part 2 of assignment 4's walkthrough, we'll see how we actually run the tests that are remote in a separate IntelliJ project, which is running in a different process or a different set of processes than the emulator that's running the client Android app. So that will actually get a chance to test things running truly remotely. As you can see, however, no matter whether you run it locally or remotely, everything should be green, indicating that all your tests pass correctly.